Hello friends. So, welcome to lecture series on essential mathematics for machine learning. In the previous lectures we have seen some of the properties of convex functions. We have seen that if Hessian matrix is positive semi definite, this implies that the function is convex on S. We have also seen about unconstrained optimization problem, that how can we find the necessary and sufficient conditions for a local minimum for a given unconstrained optimization problem. Now, what happens if a constraint is added to a optimization problem? I mean, I want to say that if it is a constraint optimization problem, what are the necessary or sufficient condition for constraint optimization problems? So, before going to the necessary or sufficient condition for constraint optimization problems, let us see some of the basic concepts of constraint optimization. So, first of all, what a constraint optimization problem is? A constraint optimization problem is basically a problem in which we have to maximize or minimize a given function called objective function, which is f here, subject to the given set of constraints. Here we are having minimum of f x, it may be maximum also. Here I am taking as minimum. The same algorithm will be followed for maximum type constraint optimization problem as well. So, if it is minimum f x subject to g I x less than or equal to 0. So, this f is basically objective function subject to m number of constraints. So, this problem P 1 here is called a constraint optimization problem. Okay. Now, there are different type of constraint optimization problem. This problem P 1, which is here, depending on the choice of the function f, depending on the choice of g i's, it may be classified in different categories. The first of all, the simplest one or the easiest one problem is linear programming problem, which we have already studied in our previous classes. What a linear programming problem is? If this f and all constraints are linear, then such problems are called linear programming problem. Okay. So, the first classification, the simplest one is linear programming problem if f and g I for all I are linear. Now, if it is not linear, that means that the objective function or at least one of the constraint is non-linear, then such problems are called non-linear programming problem or non-linear optimization problem. Okay. Now, there is a special class of non-linear optimization problem, and that special class is called quadratic programming problem. What happens in quadratic programming problem? In this problem problem P 1, if this f x is quadratic, that is of degree 2 or power 2, variables have maximum power 2 and all constraints are linear, then such problems are called quadratic programming problem. It is also a non-linear programming problem with a special feature. The special feature is that the objective function is quadratic and all constraints are linear. Okay. So, basically if we are roughly speaking, we are having two classes of two classification of such type of problem. One is linear programming, other is non-linear, and there is a special class of non-linear that is called quadratic programming problem. Okay. Now, what is convex programming problem? Now, this problem P 1 which we have just discussed, this problem P 1 is called convex programming problem if the involved objective function f as well as all the constraints, all the m constraints here are convex. That means, if f and all g i's are convex, then such problems are called convex programming problem. Okay. Now, there are different formats of convex optimization problem or convex programming problem. What are different formats? See, if this is minimization type f x subject to g I x less than or equal to 0 I from 1 to m, which is P 1 basically, then such problem is convex programming problem if f and g I for all I are convex. We have already seen this thing. But if objective function is maximization type and g I is less than or equal to 0 for all I, then this is called convex optimization problem or convex programming problem if objective function is concave and g I for all I are convex. Okay. Now, if it is minimization of f x subject to g I greater than or equal to 0 for all I, then this particular problem is called convex programming problem if objective function, that is f is convex, and all GI are concave, because inequality is reversed here. And this problem, the last one, that is maximizing fx subject to GIX greater than or equal to 0 for all I, is called convex programming problem if f is concave and GI for all I are again concave. Okay. So, basically if we understand this particular format, then we can easily derive the other format also for the that when we can say such problems are convex optimization problem or convex programming problem. So, we basically have to understand this basic format, this important format, minimization of fx subject to GIX less than or equal to 0 for all I. Okay. And if objective function as well as all constraints are convex, then such problems are called convex optimization problem. Now, linear programming problem, which we have just discussed, in which objective function as well as all constraints are linear, that is obviously convex optimization problem, because all linear functions are convex, whether the objective function is maximizing form or minimization form. Okay. So, all the linear programming problems are basically convex programming problem, but a non-linear programming problem may not be convex, may not be a convex programming problem, okay, in general. So, let us discuss a few examples which are a convex programming problem or which may not be a convex programming problem. So, let us discuss problem P1. Okay. So, what is the problem P1? It is minimization of fx, which is x1 plus x2, that is a linear function. Okay. This is a linear function here, subject to what are the constraints? The first constraint is x1 square plus x2 square less than or equal to 4, and the second constraint is x1 square less than or equal to x2 and x1 greater than or equal to 0 and x2 greater than or equal to 0. Okay. So, let us see that whether this problem is this problem we are calling as suppose P2 or P1, and we want to see that whether this problem is a convex programming problem or not. So, number one, this problem is, of course, this problem is not a linear programming problem, it is a non-linear programming problem, because objective function is linear, okay, but constraints are non-linear. So, this problem is a non-linear programming problem. Now, in order to see that whether this function, this problem is a convex programming problem or not, we first have to check objective function, and then we have to check all the constraints whether they are convex or not. Okay. So, first let us see the objective function. What is the objective function here? Objective function is x1 plus x2. What is the Hessian matrix of this function? Hessian matrix is simply 0 0 0 0, or you can directly say that since objective function is linear and the linear function is obviously convex, hence f is convex. Or you find the Hessian matrix comes out to be a null matrix, and null matrix is basically a positive semi definite matrix. So, we can say that this function is convex. Okay. Now, let us see the first constraint. What is the first constraint? G1. The first constraint G1 is x1 square plus x2 square minus 4 less than or equal to 0. Okay. What is second constraint? Second constraint is x1 square minus x2 and less than or equal to 0. Okay. What is third constraint? Third constraint is minus x1 and it is less than or equal to 0. What is fourth constraint? Fourth constraint is minus x2, which is less than or equal to 0 again. This x1 greater than or equal to 0 we can write as minus x1 less than or equal to 0. So, how many constraints we are having in this problem? We are having 4 constraints, and if all the 4 constraints are convex, objective function is already shown that it is convex. So, if all the 4 constraints is also convex, then we can say that this problem is a convex programming problem. So, let us see the first constraint. The first constraint is G1, and what is G1? G1 is x1 square plus x2 square minus 4. Let us find the Hessian matrix of G1. The Hessian matrix of G1 will be 2 because we have to do the second derivative with respect to x1. Okay. Then x1 x2 0, x1 x2 0, then it is again 2. Okay. So, its eigenvalues are 2 and 2. Okay. Either you can see eigenvalues or principal minors. So, principal you can find the minors also. So, minors of order 1 cross 1 are 2 and 2, and minors of order 2 cross 2 are determinant of this matrix, and determinant of this matrix is 4. So, all the minors are strictly greater than 0, that means this matrix is positive definite and hence convex. So, this implies this Hessian matrix is positive definite and this implies strictly convex or convex. So, we can say that G1 is convex. Okay. Now, so first constraint is convex. Now, what is the second constraint? See, what is the second constraint? Second constraint is x1 square minus x2. Now, similarly, let us find for the second constraint. So, the second constraint is x1 square minus x2. So, what is the Hessian matrix of G2? It is 2 0 0 0. So, again if you use the minor test, so minors of order 1 cross 1 are 1 cross 1 are 2 and 0, and minors of order 2 cross 2 are 2 cross 2 is because there is only one minor which is determinant of this, which is 0. So, this all the minors are greater than equal to 0 implies this Hessian matrix is positive semi definite, and hence we can say that G2 is convex. So, this implies G2 is a convex function on R2. Okay. Now, what is the third constraint? The third constraint is linear minus x1, which is obviously convex, and the fourth constraint minus x2 is also linear, which is also convex. So, hence we can say that the objective function as well as all constraints for this problem P1 are convex, and hence we can say that this problem is convex programming problem. Okay. So, the example 1, the problem 1 is basically a convex programming problem. Now, let us see for the problem 2. For the problem 2, what is the objective function here? Objective function is 2 x1 minus x2, which is linear, so it is concave, because for maximization type we should see that f should be a concave function. Then see, we have already seen that if it is a maximization type problem, then f must be a concave for a convex programming problem. So, it is concave as well as convex. So, it does not matter for this linear part, otherwise we should see that this function is concave. So, that is concave. Now, the first constraint is x1 plus x2 minus 3 less than equal to 0, which is linear constraint, hence convex. Okay. So, let us see this thing here. For the problem P2, is maximization of f equal to 2 x1 plus x2, okay, 2 x1 minus x2, sorry, it is 2 x1 minus x2, subject to what are the constraint? First constraint is x1 plus x2 minus 3 less than equal to 0, this is G1. Okay. The second constraint is x1 x2 less than equal to 1. The second constraint is x1 x2 minus 1 less than equal to 0. Third constraint is minus x1 less than equal to 0. Fourth constraint is minus x2 less than equal to 0. So, this is linear. This is linear means convex as well as concave here, convex and concave. Okay. This is linear means it is also convex. This is linear, so convex. G3 is also convex, okay, and G4 is also convex, because linear functions. Now, we need to check only for G2. So, let us see whether G2 is convex or not. If it is convex, then it will be a convex programming problem, otherwise it will not be a convex programming problem. So, what is G2? G2 is x1 x2 minus 1 less than equal x1 x2 minus 1. Okay. So, here it should be, yeah, okay. So, what is Hessian matrix of G2? It is second partial derivative is respect to x1 for g2 which is 0, it is 1 1 0. So, minors of order 1 cross 1 are 0 and 0, and minors of order 2 cross 2 are 0 minus 1 which is minus 1. So, this make it indefinite. Okay. So, this matrix is this Hessian is not positive semi definite, and hence this function is not convex. So, this implies G 2 is not convex. So, what we have concluded? See, in this problem this is convex and concave both, this is convex, G 4 is convex, but G 2 is not convex. So, this implies that this problem P 2 is not a convex programming problem, because objective function as well as all constraint must be convex. Okay. For minimization type objective function is all constraint less than equal to type. So, hence we have concluded that P 1 is this problem is convex and this problem is not a convex programming problem. Now, we have an important result for this, that if G I for each I are convex functions, then this set is a convex set. Okay. So, let us proof is very easy, you can see that we are constituting all those x in R n such that G I x is less than or equal to 0 I from 1 to m. So, this is basically what? This is basically a feasible set or a feasible region, okay, satisfying all the constraints. Now, it is given to us that all G I's are G I's for all I's are convex functions. It is given to us. Okay. And we have to show that this set S is a convex set. So, how we can show this set is a convex set? You can take two arbitrary point in S and try to show that the convex linear combination of those 2 points is also in the same set. So, let us see, let x 1 x 2 in S. So, this implies G I x 1 is less than or equal to 0 for all I, and G I x 2 is also less than or equal to 0 for all I. Now, let z equal to lambda x 1 plus 1 minus lambda x 2, which is convex linear combination of x 1 and x 2. Now, what is G I z for any I? It is G I lambda x 1 plus 1 minus lambda x 2. Now, these G I's are convex for all I. So, this means this is less than or equals to lambda G I x 1 plus 1 minus lambda G I x 2, and G I x 1 is less than or equal to 0 for all I, G I x 2 is less than or equal to 0 for all I. So, this is less than or equals to lambda into 0 plus 1 minus lambda into 0 is equal to 0. So, this implies G I z is less than or equal to 0 for any I, and this implies z belongs to S, and this implies S is a convex set on R2 Rn, convex set. So, what we have seen? We have seen that if we are taking a convex programming problem, then the feasible region of a convex programming problem is always a convex set. Okay. So, that is the important property. See, in this example, if you draw the graph of this, so it will not be a convex set. The region is not a convex set. That is why it is not coming out to be a convex programming problem. So, before going ahead, let us first come to quadratic programming problem. So, we have seen that a quadratic programming problem is basically the objective function is quadratic and constraints are linear. Okay. So, suppose you are having this type of problem, minimizing 2 x 1 square minus x 1 x 2 plus 4 x 2 square plus 6 x 1 plus 8 x 2. subject to 3x1 plus 2x2 less than or equal to 6 and x1 x2 non-negative. A simple problem I have taken to understand. It is a non-linear programming problem, and this non-linear programming problem basically a quadratic programming problem because the objective function is quadratic and all constraints are linear. Now, if you take this problem f, so you can write this problem as x1 x2, okay. This 2 will come here, this 4 will come here, this is minus 1 by 2, this is minus 1 by 2, this is x1 x2 will come here, this is 6 and 8 and this is x1 x2, and subject to this is 3 2 x1 x2 less than or equal to 6 and this is x1 x2 greater than or equal to 0 0. So, if you take this as capital X, okay, so this will be X transpose and this you can take as Q. So, here I have taken half, okay. If I have taken it half here, okay. So, if I have taken a half here, so I can take it half here and I multiply this by 2. So, in that case it will be 4 8 minus 1 minus 1. So, it is 1 by 2 x transpose q x plus this is C transpose, this is x, this is matrix A, this is x, this is B and this is x greater than or equal to 0, this is 0. So, what I want to show, I want to illustrate you that any problem of this type which is having quadratic objective function subject to linear constraints can be written in this format, which is C transpose x plus half of x transpose q x subject to A x less than or equal to B x greater than or equal to 0. Okay. So, here this q is what? If you carefully see what q is, this q. What is the Hessian of this f? If you compute the Hessian of this particular f, so Hessian matrix of this f will be, you have to differentiate with respect to x1 twice. So, that will give 4 minus 1 8. So, which is here. So, this q is nothing but Hessian matrix of f for this type of QPP. Okay. Now, the interesting question is that when this problem is convex programming problem. See, constraints all are linear. So, we are not worrying about the constraints are linear. So, these are obviously convex, but what should be the restriction on f, on C or Q, so that we can say that the given problem is a convex programming problem. Okay. Now, why we are focusing on convex programming problem so much, that we will discuss in the next lecture. Okay. So, first we will see that when we can say that this problem is a convex programming problem. So, to understand this we have two important results. The first result is, if this M is a symmetric positive semi definite matrix of order n, then for any x y in R n this inequality hold. The proof is very easy. See, the proof is easy. See here what is given to us, we are to given that M is a positive semi definite symmetric matrix. Okay. So, we have to show that x transpose m y for any x y in R n is always less than or equal to 1 by 2 times x transpose m x plus y transpose m y. If it is a positive semi definite matrix, so for any x y in R n, x minus y transpose m into x minus y. See, x minus y is also a vector in R n, and if it is a positive semi definite matrix, then x transpose m x is always greater than or equal to 0 for any x in R n, and this x minus y is also a vector in R n. So, for this also this is greater than or equal to 0. because M is positive semi-definite matrix. So, what does this implies further? This further implies X transpose M x plus Y transpose M y minus X transpose M y minus Y transpose M x get equal to 0. Okay. Now, let us, so this is required in the proof. If you see the proof, this is required here. So, now let us focus on this part. So, what is Y transpose M x? Now, let us see. Let us see here. What is Y transpose M x? Y transpose M x is basically a real number, a scalar number. It is in R. If it is in R, so it will be equal to its transpose. Okay. So, what is equal to X transpose M transpose Y, and M is a symmetric matrix also. So, symmetric means X M transpose is equal to M. So, this is equals to X transpose M y. So, that means this is equal to this. So, this further implies using this X transpose M x plus Y transpose M y minus X transpose M y minus X transpose M y greater equal to 0, because this is equal to this we have just shown. So, this implies X transpose M x plus Y transpose M y is greater than equal to 2 times X transpose M y. So, hence we have done, hence that if you take this to this side, so hence we have proved this result. Now, this result is required to prove the next result. The next result is a quadratic programming problem is a convex programming problem if Q in the objective function is positive semi-definite matrix. If this Q here is positive semi-definite matrix, then this problem QPP will be a convex programming problem. So, how can we show this? How can we show this result? So, the again we will the proof is easy. So, what is the objective function here? Objective function is C transpose x plus 1 by 2 x transpose q x. To show that this function is a convex function, let us take 2 point x 1 x 2 in Rn and take the CLC of these 2 points and take the CLC of these 2 points. The CLC will be equal to this and will be minus lambda. See, what I am trying to do here, we have to show that this f is convex. So, to show that this f is convex, if we apply the basic definition of convexity, then we have to show that this quantity is less than equal to lambda f x 1 plus 1 minus lambda f x 2. So, that means I have to show that this quantity is less than equal to 0. Okay. So, I have taken this expression, I will try to show that this is less than equal to 0 if Q is positive semi-definite matrix. Okay. So, now let us quickly substitute all these values from given f. This is f x. So, this is lambda x 1 plus 1 minus lambda x 2, and then it is plus 1 by 2 lambda x 1 plus 1 minus lambda x 2 whole transpose q into lambda x 1 plus 1 minus lambda x 2 minus lambda times x 1 minus 1 by 2 x 1 transpose q x 1 minus 1 minus lambda times c transpose x 2 minus. So, this lambda will come here also. So, it is 1 minus lambda times 1 by 2, it is 1 minus lambda f x 2. So, it is x 2 transpose q x 2. Okay. So, this lambda is a scalar quantity, can be taken out. So, this will comes out to be C transpose x 1 lambda times. So, this will be cancelled with this term. This 1 minus lambda again will come out. So, it is C transpose x 2. So, this will cancel with this term. Okay. We are left with these terms. So, 1 by 2 can be put common in all the terms, and let us simplify this expression. So, it is lambda square x 1 transpose q x 1, because lambda is a scalar quantity, plus 1 minus lambda square x 2 transpose q x 2 plus this is lambda into 1 minus lambda x 1 transpose q x 2 and plus lambda into 1 minus lambda x 2 transpose q x 1 minus lambda times x 1 transpose q x 1 and minus 1 minus lambda times x 2 transpose q x 2. So, these are final expression we left with. We anyhow we have to show that this is less than equal to 0 in order to show that this function is a convex function. And we have to use that Q is symmetric positive definite matrix, positive semi definite matrix, this we have to use. So, now let us see. Now, from this and this what is common? From this and this lambda is common, x 1 transpose q x 1 is common, this is left with lambda minus 1. Again from these two x 2 transpose q x 2 is common and this is 1 minus lambda is also common. So, it is 1 minus lambda minus 1 and leave these two term as it is, lambda 1 minus lambda you can take common, x 1 transpose q x 1 plus x 2 transpose q x 2. Okay. So, this 1 cancels out. So, lambda into 1 minus lambda is you can take common from all the 4. So, what we get? We left with lambda into 1 minus lambda upon 2. Okay. It is what? Negative can come out. So, it is minus x 1 transpose q x 1. What is the second term? Second term will come from here, which is minus x 2 transpose q x 2. Okay. And then from here it is it is x 1 transpose q x 2. So, this will be x 2 and it is x 2 transpose q x 1. So, x 2 transpose q x 1, it is x 1. See here, it is x 1 transpose q x 2, it is q x 2, it is q x 1. Okay. So, it is plus x 1 transpose q x 1 q x 2 plus x 2 transpose q x 1. Now, you can make use of that lemma, that result which we have just discussed, this result, that x transpose this twice of this is less than equal to this, because you see here, because these two are equal, we have just shown these two are equal. These two are equal means this can be written as lambda into 1 minus lambda upon 2 times minus x 1 transpose q x 1 minus x 2 transpose q x 2 plus 2 times x 1 transpose q x 2. Okay, because these two are equal. So, this expression from that lemma will be less than or equal to lambda into 1 minus lambda by 2. This whole quantity is 0, less than or equal to 0. So, it is 0 by this result, whole quantity is less than or equal to 0. So, hence we can say that this function is convex if Q is symmetric positive semi definite matrix. So, whenever we deal with quadratic programming problem in developing algorithm for machine learning, then if we have to see that whether a given QPP is convex or not, we have to simply work out for Q. You simply try to find out the Q and try to see whether that Q is positive semi definite or not. If it is positive semi definite, then the given QPP will be a convex programming problem. So, for illustration here are examples. So, let us discuss the first example. So, constraints are linear. So, no, we are not worrying about the constraints, we have to find the Hessian matrix of this Q only. Okay. So, what is the Hessian matrix here for the Q? So, for the first example, what is Q? Q is nothing but Hessian matrix of F. So, what is Hessian matrix here? Diagonal elements will be 2, 4, 9, 2, 4, 6, sorry, it is 2, 4, 6 and it is 4 x 1 x 3, 4 x 1 x 3 means 4 will come here, 4 will come here. Then it is 2 x 2 x 3, 2 x 2 x 3, x 2 x 3 means 2 will come here, 2 will come here, this is 0. x1 x2 is 0, okay. Because other part is linear. So, Hessian will be 0 and from x1 x3 x2 x3 that only these terms will be there. Now, to show that it is symmetric, okay, and we have to just show that this Q is positive semi definite matrix. So, find the minors of this Q. So, minors of order 1 cross 1 are simply 2 4 6, minors of order 2 cross 2 are determinant of 2 0 0 4 which is 8, determinant of 4 2 4 2 2 6, okay, which is 24 minus 4 is 20 which is positive again, and it is 2 4 4 6 which is 12 minus 16. So, this row and this column will be deleted, 12 minus 16 which is negative. So, this is not a positive semi definite matrix, and this problem, hence this problem is not a convex programming problem. So, similarly one can show that so this problem is not a convex programming problem. However, this, if you find the Hessian matrix of this, so one can easily show that this is convex programming problem, because the Q will be positive semi definite matrix. If you are having a quadratic programming problem and you want to show that it is a convex programming problem or not, you simply find out the Hessian matrix of that f, that objective function, that is nothing but Q, okay. And if it is come out to be a if it is come out to be positive semi definite, that implies that is sufficient to say that the given QPP is a convex optimization problem. So, in the next lecture we will see that if it is a general nonlinear problem, then how we can say, then how the convex programming problem are important. So, thank you.